It's not Michigan time yet. We have a few more minutes, but I thought maybe we can get started. And I'd like to welcome you to this very special guest lecture. I'm Khalil Najafi. I'm the chair of electrical computer engineering. I'd like to welcome you all. As I said, this is a very special lecture. That's why we called it such, a special guest lecture. It's, I think, the title that we've used only once. And this is to introduce Professor Ernest S, who's the William S. Floyd Jr. Professor Emeritus in the Department of Electrical Engineering and Computer Science at the University of California at Berkeley. Professor Ku is widely recognized as a pioneering scientist and engineer who's had a huge influence on the early development of circuit theory and electronic design automation of large-scale integrated circuits and systems. I'm also delighted to add that he's an alumnus of our department, and so that's why it makes it special, not only because it's a special role in electrical engineering development, but also because he's an alum of our department. He graduated with his bachelor's degree in electrical engineering in 1949. He then received his master's from MIT and his PhD from Stanford. And then worked for Bell Labs for a little while and was hired by Berkeley, where he spent the rest of his professional and academic career. At Berkeley, he served 4 years as department chair, and then, like our own dean, Dave Munson, he was appointed dean of the College of Engineering. Professor Ku has seen a lot in his lifetime. And sometimes we like to read your memoir, Ernie. There's a lot that you have done for the discipline and for the field. And through your research, he's had his hand in shaping the future of electrical engineering and computer engineering. He received the Phil Kaufman Award for his contributions to electronic design automation, as well as for his role in mentoring a large number of students who were important to further developments in our field of electrical and computer engineering. Professor Ku excelled as an educator. He wrote several widely used books in the areas of circuits and systems and received the IEEE Education Medal for his leadership in engineering education. Just a few years ago, he received the Kirchhoff Award for his contributions to circuits and systems and to electronic design automation in electrical engineering. He was inducted into the Silicon Valley Hall of Fame. He is a fellow of the IEEE, a fellow of the AAS, a foreign member of the Chinese Academy of Sciences, and a member of our own National Academy of Engineering. I can go on and on, but I think it's much better for you to hear from him directly instead of me talking about stuff. And so I'd like to welcome Professor Ernest Ku to this special lecture.
Thank you so much for your generous introduction. I prepared some slides I will show later, but I think I will say something about the past, about myself, and what I did in my career. I only had 2 jobs in my career, 4 years at Bell Laboratories, and since 1956 at UC Berkeley. Both are exciting places and rewarding to me. I will jump around from Bell Labs to UC Berkeley. At UC Berkeley, I enjoy very much teaching and research, working with students and in administration. Also working with industry. So let me start on the industry first. since Berkeley is close to Silicon Valley, one day I got a phone call from this company, ECAT, I guess electronic CAD. Because at that time, most of the CAD work was mechanical. So that's why the name of the company is ECAT. And soon I was asked to serve on the board. And soon that company merged with a company sponsored by the National Semiconductor and became Cadence Design. I served on the board of Cadence for 3 years and established their scientific advisory committee. I invited my colleague, Richard Newton, to chair that committee. I think we did a lot of good to the company, and they listened to us. Cadence is much larger now. It's over $1 billion in revenue. I don't remember how much is their income. Anyway, a very successful company, together with Synopsys, the 2 top companies in the field. Now let's go into students. I enjoyed very much teaching, as I said. I supervised by myself 40 PhD students. And many of them are all over the world: Asia, China, Japan, Korea, Europe, South America. So sometimes I get to see them. I just want to mention 2 who are the closest to me, and they still come to see me. One is called, both are Chinese, but I have many American students, Indian students too. One is Qiping Xu. He did his thesis with me. Such an outstanding thesis. I gave him the PhD in 2 years. I don't want to hang on to students like MIT does. They keep their students forever. When I served on the MIT advisory committee, I told them, you better wise up. And I think they listened to me. They found a second degree called the Master Engineering and a second track from Master Science to speed up the PhD work. The second student I see often is called Wen Dai. He's quite different from Qiping Xu. Of course, he was very good in research, but shortly he decided to form his own company. His company is called VLSI because to start with, to verifying circuits. And shortly he expanded his business. He has his headquarters now in Silicon Valley and in Shanghai, China. And then he bought part of Fairchild, so he has a branch in Texas. And soon he established a branch in France, a branch in Germany. So he travels all over. But he still comes back to see me, so I appreciate that. So those are the 2 students I'm closest to. Next, I want to talk about sabbatical leave. I never missed a single sabbatical leave. Even during the time I was department chairman and dean, I told the Chancellor Albert Barker, I'm not going to forget my sabbatical leave. I'm not going to take summer time as chairman and dean. So we always appointed somebody as acting, and that really helped. So during sabbatical, we enjoyed the most time at Imperial College in London. Actually, I visited London maybe 4 or 5 times, that spent time there. I also spent time at Technical University of Munich. Munich is a wonderful city, close to ski resorts, We used to do hiking. Actually, I went to Munich several times because I got a 1-year so-called Ernest S senior postdoctoral fellowship. They allowed me to spread it up into 3 periods. So we visited Munich more than 3 times. Of course, we traveled to 2 countries we really enjoyed, Italy and Switzerland, to see sites. One of my sons worked at London for 9 years. And so we often visited him, and he had a car. He drove us, my family, and even my other son, to places all over in Italy, and then to Switzerland. So these are the fun times. So much for traveling. What's the next subject? Next subject is to get into administration. After 1956, in 1968, I succeeded Professor Lockheed as department chairman. I served for 4 years, and during that time I traveled to Japan for my sabbatical. 1973, I was called to the chancellor's office. I was surprised he offered me to be the deanship. I hesitated. I said, I'll tell you later. But it didn't take me long. The next day I go to see him, and I told him I accepted. It's a challenge. I thought I can do something new and different. So I told the chancellor I want to do my own fundraising. So I started fundraising, and for one thing, established an engineering program called the Berkeley Engineering Fund. And that was helpful for spare money I need to operate the college. But most important, it was the industrial liaison program. With that, I got to know many companies, except the company leaders. First, I got to know the famous builder, Stephen Bechtel. For those who don't know, he is the biggest builder in the world. Not only in the United States, in the Middle East. And he helped me through his friends, his family, to build the Bechtel Engineering Center at Berkeley. I got to know Pacific Gas Electric Company president, and Sherman Sibley. So now there's a Sibley Auditorium in the Bechtel Center. When we have meetings, we have in Sibley Auditorium. So that facility is being used not only by engineering, but by other colleges at Berkeley, because at that time, nobody had such a beautiful facility. Recently, they remodeled the place. Here is a very nice place. Now I haven't seen the new place. What's next? So much for that. Let me go back to Bell Labs time. I worked at Murray Hill, New Jersey. Bell Labs was the place to go for all electrical engineer PhDs. It was not easy to get in, but my professor at Stanford knew somebody helped me to get in. I still remember my starting salary was $600. That was enough for a bachelor, and I lived in a rooming house. But at Bell Labs, I got to renew my friendship with my former classmate at Stanford, Don Peterson. For those of you who haven't heard the name, Peterson is the person developed the famous SPICE program. I think every electrical engineer probably run into SPICE. And there are now different versions of SPICE. Also, Don Peterson is the guy, he did not want to keep anything confidential. He released it to the public. So that made SPICE even more popular. And with Don Peterson, I wrote the first book, textbook, called Principles of Circuit Synthesis. And that book has been translated to many languages, including Russian, Italian, French, of course Chinese and Japanese. But now, of course, it's out of date. Now, my second best friend is Charlie Desor, my classmate at MIT. Happened at Bell Labs, both Peterson and Desor were assigned to the same laboratory, the Transmission Network Laboratory. So we worked well together. I managed to publish, I remember, 4 papers during that period. But what's more important, I got to know some famous people at Bell Labs, including Hendrik Boddy. I think many people know of his work in control theory, in networks, including David Slappy, expert in communication theory, including Sidney Darlington, expert in circuit theory. I remember when I took the course from Professor Gilliam at MIT, he taught us the Darlington method of synthesis. And he was a great friend later on. I never got to know Claude Shannon. I saw him running in the hallway at Murray Hill, always has his head down, thinking. I never got to know him. I got to meet Bill Shockley, a Nobel Prize winner. He later went to Silicon Valley, I think funded money by the Sherman Fairchild. And from that, there's a Fairchild semiconductor company. And from that, there was Intel. Intel dominated the world in microelectronics. So the work at Bell Labs created many benefits. Okay, back to Berkeley. As I told you yesterday, I came to Berkeley in 1956. I got involved in teaching, research, writing, and many other things. And I got interested in writing. So together with Charlie Desor, we wrote 2 books on circuit theory, which became very popular, even though it's out of date. But you're amazed, I'm amazed to see that translation or the original version is still being used in many countries, even now. So that's my teaching, research, and activities. Let me check my watch. I don't want to spend too much time. So maybe I'd come back to Bell Labs. When I was at Murray Hill, New Jersey, there's a director of the Whitney Laboratory. He did some outstanding work in network synthesis. So he knew my name. So he invited me to visit him. And Macmillan later on see, Whitney does all the military work. So he was invited to join the administration. He served as the Secretary of Air Force. And then he retired to the Bay Area. And we saw him several times not too long ago. But at the Whitney Laboratory, he showed me this interesting project. That is the design of the multiple layer printed circuit board. But they didn't quite know how to do it. So everything was by intuition, by cut and try, nothing systematic. So back to Murray Hill. See, I am more close to mathematics, and I learned the graph theory, and I found that's very interesting. So I want to formulate the problem in the simplest way so that we can design things not by cut and try. So that started with the first slide. Let's see, I have to use which one?
Space for it.
Oh,
There, oops.
oh, that's good.
There, that's it.
Okay. Did we show the title?
Yes. Yes.
Okay. Okay, this is called single routing. You have a set of pins. I don't have a pen here. Can I borrow a pen from you?
You want the pen or you want a laser pointer?
No, I just want to point here.
Oh.
Will that show up?
No.
No.
Laser pointer on the
Okay.
screen.
Okay. This is a single row with points equally spaced on this real line. Some are connected to this net. So it's a very simple problem, and the objective is to minimize the height, because that corresponds, in the two-dimensional case, the area of the chip. So we want to minimize this height. So that turned out to be an interesting problem. I learned graph theory at MIT. We use graph theory, and that was helpful. See, next slide, which one?
Just the space bar.
Oh, well, sorry. This is so-called point modules. As you can see, modules equally spaced in 2 dimensions. So the problem here is to place the module at the right place and then do the routing. And at that time, in Silicon Valley, gate array was implemented and useful. So we introduced some algorithm to do the optimum placement and routing. Now this becomes more difficult. You have point modules plus irregular shape, finite area modules. So how to design this in an optimal way? That's a tough problem. And people in computer science talk about NP complete. This is certainly not. So, to show you this is a real layout system. And this is the blocks. So it's shown here. We developed at Berkeley the BEAR building block layout system. This is a typical industrial example. And later on, a better program is called BEAR 2. And this example, 33 blocks, 123 nets, placement with routing area estimation, because you have to estimate the area you need between the blocks and then do the routing. Okay, now here's some graph theory which is useful. Now this is a typical chip. This is a chip which you cannot slice across. So it's more complex. So for this chip, it's represented by this tree. See, you can start from the top, which represents the whole thing, and the sub-blocks, this one, and this one represents this side, and then this side is this block, and so forth. So this is the block representation, this design. And I have the, let's see what's the order. Then we have to do the routing. Which areas you're going to route first? See, there's the routing area. So there's a problem representing the slicing structure, and then the T-junction of two channels. This, for example, is T-junction. This is not. My hand shakes, so I hope you can see it. And this, again, graph theory terminology, so I will skip that. So this represents the non-slicing structure. And this is the inner dual graph of the graph. And then for each submodule, you have representing by either horizontal line, vertical line, and at different places, and so forth and so on. So floor plan templates for 2-room, 3-room, 4-room, 5-room configuration. Okay, this is a big tree which represents the whole structure. You can see that each sub-blocks and sub-sub-blocks. And a sub-block, for example, represents these modules. Another one at this size, another one this. So you can have different shape in order to fit better. Okay, so much for floor planning. So let me say something about routing. Routing area exit allocation. This is the routing area between blocks. That's a routing area. At that time, you can only have 2 layers for routing. So we developed a very nice algorithm called channel routing. Actually, we worked together with Bell Labs on this subject, and very interesting problem, and we published papers on that. Just to show you some terminology, in order to connect those 3 points in the rectangular grid, this is called Steiner tree, a Steiner point, which is the shortest distance. Half parameter wire length is equal to the length of a Steiner tree for 3-terminal net. S is called a Steiner point. Another terminology I want to introduce, so for the minimal spanning tree. This is a minimal spanning tree to connect these 4 points, but there are different ways of connecting them. So for those of you who know something about graph theory, I think this may be interesting. Drink some water. Later on, I worked with my former students, Professor C.K. Cheng at UC San Diego. He is still there. So we worry about technology trends with wires as resistance capacitance lines. As the technology scales on chip, interconnection has become dominant factor. of the system performance and power dissipation. Treating on-chip global wire as transmission lines, that's the way to do it. So we worked that with the UCSD group to treat on-chip global wires as transmission lines for speed of the light communication. Changes of transmission line signaling in the future as the bit rate increase well into the tens of gigahertz range. Energy dissipation and signal integrity become crucial factor of the performance on the chip, of on-chip interconnect. Interconnect at architecture level with a continuous appearance of new computing architectures, design objectives or matrices to guide on-chip interconnect optimization has to be revised. Clock signaling problem, distributing multiple gigahertz clock signal with low jitter and skew and low power consumption has become a challenging design task for microprocessor design and high performance VLSI chip. I guess that's the slide made some time ago, so it's no longer a challenge. Propagating clock as waves as an alternative clock approach, wave-based oscillator having intensely studied recently. There's some mistakes here. Interconnect analysis was done by two people. I mentioned Chi-Ping Xu at Cadence Design. He's the doctor. Professor Andreas Kuhlmann at Berkeley. He is a consultant with Cadence. The performance of CMOS design is mainly determined by the longest delay of any combinatorial path from the circuit's primary input and latch output to its primary output and latch inputs. This terminology is familiar to the electrical engineers. Starting in the mid-90s, interconnect delay started to increasingly matter. Historically, the first approach to this compact delay model from the distributed RC model was based on Elmore delay model. Essentially, it's a first order approximation. As the interconnect structure scaled down, capacitance coupling between interconnects started to impact their delays, and the so-called crosstalk needed to become modeled and considered. With further shrinking feature size, process variation become increasingly relevant and needed to be modeled. And this is especially important for manufacturing. Oh, that's the last slide. Maybe I spoke too fast. I lost some time for questions. Now for people who are not familiar with what I taught, everybody should know Ohm's law. Now this graph shows the relation of a resistor, but it's not an ordinary Ohm's law resistor. It's a nonlinear resistor which relates voltage, current, and time, nonlinear time variable. This is the inductance which relates the flux, current, and time. This is the nonlinear capacitance which relates charge and voltage and time. So we put a symbol like this to indicate it's a nonlinear. And my colleague, Professor Leon Chua, introduced memristor. So he asked the question, you have the four things here, but what's the relation between charge and flux? He introduced the name memristor. That's the symbol. Memristor was not popular because it's a theoretical model until Hewlett Packard, oh, I forgot his name, somebody new told me. Stanley Williams. You know that. Stanley Williams did some work at Hewlett Packard and implemented a practical model of memristor. He published a paper in the Journal of Nature, which is like a science journal, and that made memristor popular. And not only that, because a memristor with the Williams model, they can design multiple layer circuits with memristors. So that's the story of the relation to printed circuit board design, multiple layers, and the memristor boards. So this concludes my talk. I guess I spoke faster than I should, and I'd be happy to answer any questions.
So this will leave us more time for questions, but before questions, Professor Koo mentioned a couple of things that I'd like to maybe talk about. First, you said that you graduated your PhD student in 2 years. I see some of my students here and some other PhD students don't expect to graduate in 2 years. Don't come to us asking for 2-year graduations.
You should change.
And you talked about sabbaticals, and our dean is here, so maybe you should make sabbaticals every 2 years, Dave.
Well, if you have a quarter system, you can make it.
Yeah. See? Anyway, questions?
What did you think of Shockley when you talked to him or met him at Bell Labs?
Well, he was a genius, but he was also a character. So of course he created the industry of Silicon Valley, but later on he caused a lot of problems. Some of you may be familiar with the problems he caused. So his reputation has been changed afterwards, and people don't think him as a great person anymore. So that's the impression, but there's no question his contribution to science and technology was tremendous. He won the Nobel Prize for that. I should mention Bell Labs is a unique place. It has won 7 Nobel Prizes, and no place, maybe IBM has caught up. And one at Bell Labs, the telecommunication, Telstar. I don't remember the others. But unfortunately, Bell Labs disappeared. That was truly a tragedy. Together with Western Electric, the manufacturing arm of AT&T, and ATT itself. The AT&T now is not the same AT&T of that time. AT&T now is the combination of 2 operating companies, and it's much smaller. And so that's the story about Bell Labs, Western Electric, and AT&T. And most of the people so much younger than I am did not know that story. Next question, yes?
So you took classes with Professor Gilliman, right?
Yes.
How was that?
He was the greatest teacher I ever had. I was fortunate to take the class when I first went there, and my classmate was Charlie DeSore. And we did not have to work too hard because he was so good teaching. explained everything so well. So I asked him to be my thesis advisor for my master's degree. And he was a very kind person, gave me the direction, and I finished that after the summer. Then I went to Stanford.
His books are not that easy to read anymore. They're very complicated.
Oh, it's a wonderful book, but this kind of thing is totally out of date because you talk about synthesis is for simple passive circuits. Who deals with RLC circuit anymore? Nobody. Especially with active devices, with digital circuits. So you don't talk about that anymore. So nobody knows about network synthesis. Yes.
So at the University of California, Berkeley, you talked about some of the companies that were
Yes.
started or based on a lot of the technology or research that was done. And of course, Berkeley has been very successful. Can you talk about what were the things that made it maybe so much easier for both faculty or some of the students to start these companies and for these companies to really become very successful? Was there a special, treatment that Berkeley or faculty
I
applied?
guess I don't want to be modest. I started the industry liaison program when I was dean. I encourage people to work in industry. I got to know the leaders in Silicon Valley, and they accepted those students, and they took courses offered by us. So that started this close relation between Berkeley and Silicon Valley. Of course, Stanford had advantage being right there, being the Hewlett Packard was former Fred Terman student, so they also had very close tie with industry. And MIT at that time had a few companies nearby, a digital computer company and others, and so they had their ties. So these are the three places that had very close ties with industry. Yes, please.
Yes, what should we teach to students for their first electrical engineering class? RLC circuits?
What is it again, the question?
What should we teach in the
Oh.
first electrical engineering course to our students?
First electrical engineering class. Well, of course, you still have to keep analog circuits as a background. So we have to start with Kirchhoff's laws, Ohm's laws, but you should go into more advanced topic. Active circuits, transistor circuits, and then more importantly, digital circuits. So what you talk about is important at high frequency, but the emphasis should be now more in the digital electronics.
Any other questions?
Yeah, Ernie, when you started at Berkeley, was Berkeley at that time viewed as one of the very most preeminent universities in the United States? And if not, what took place to get it there?
Oh, no way. Berkeley was not well known. Certainly MIT, Stanford, much better in reputation. I think the period when John Winery, former department chairman and dean, who wrote a famous book, Raymond Winery on field theory. It's a very difficult book, but I certainly learned a lot from that book. When Winery was the dean, he first hired Don Peterson I think that's a key appointment. And then he interviewed me. At that time, interviewing was not done by visiting the campus. We were just sitting in the Hilton Hotel, have a drink. So he offered me the job. So Winery was a key player to develop Berkeley's reputation. And second key factor was the period when Don Peterson joined it, when I joined it, when Charlie DeSore joined it, when Lotfi Zadi joined. Then Berkeley become top-notch, and that's the time the reputation really changed. Yes?
Do you have any words of wisdom for graduate students when you were a graduate student?
Oh, study hard. Don't listen to your advisor all the time. Challenge him or her, whatever he said. And do a lot of reading. Yes?
What if he's standing next to me?
What?
What if he's standing right next to me?
What if her advisor is standing right next to her?
Oh, he heard it. Any other questions? Well, thank you very much.
Thank you so much for your guest lecture. We just framed the poster that we posted around
great.
advertising your lecture.
Yes.
Just as as something to remember.
Thank you very much.
But I also just put this down here. I also wanted to. Many of you were not present at the special lunch that we had yesterday. For those of you who might not know, I wanted to mention that Professor Ernest S and his wife Bettine have also endowed a very special position in our department for a Distinguished Faculty Scholar Award. And this endowment, of course, will go on forever and will fund essentially one of our junior faculty that has taken a leadership or position and is very innovative. We had this special lunch to not only recognize Professor Koo and Bettine, but also to appoint the first holder of this position, who's Professor Tony Gerbic, who many of you know. So it was a very special event. We very much enjoyed having Professor Koo, Bettine, and many of the members of the family, a number of our faculty, and so forth. But we also wanted to make sure that the rest of you in the department, many of you, of course, are students, some working with Professor Koo, Professor Gerbic, and others, realize that this is a very important gift to the department. We also wanted to recognize Professor Koo and Bettine. So for that, I'd like to ask Bettine if you can come up here. We have a very special gift, and Dave, maybe you can come up here also. Just, Professor Koo mentioned yesterday that he's, one of the first experiences he had when he came to Michigan was he learned American football, and also that he learned how to play football and so forth.
Not to play.
Not yet.
I used to play soccer.
Yeah. So actually, maybe we can bring you over there. We have
Well, I have
a
to
special.
hold on to this.
Well, maybe you can go right that
We can
table.
bring this over.
Yeah. A special gift for you. So we're gonna remember you forever.
Thank you.
But we would like you to remember us forever. And there's a good way to remember Michigan. Yeah, maybe you can. Happy here.
Oh my God.
Yeah.
I will give that to my youngest grandson.
There's a writing here
There's
that
a
I'd like to
plaque
read,
here.
yeah, that
Yeah.
says, in appreciation for the endowment of the Ernest and Bettine Coup Distinguished Faculty Scholar Award for Electrical and Computer Engineering at Michigan 2012.
Thank you.
All right.
Thank you.